Right, it's time to quieten down, and we'll get started with lecture 13. And we're going to talk today, we're going to finish off talking about weather and winds, and I've got an example to show you of today, because today we are actually being affected by weather, which is unusual for us. And so I have some maps to show you of what's happening today, why we're getting cold weather and rain. So hopefully a whole bunch of you are watching that video that I showed at the beginning, and that's actually not observations, that's actually a climate model that runs, and it shows the circulation of the winds and also the distribution of clouds. And you can see that there were very distinct patterns that we saw sort of spread over the different latitudes, and we're going to come on today to talking about why we see those different patterns. Okay. Time to quieten down, please. So one of the things that people asked me for in the midterm evaluations was more specific ideas of reading. So today's lecture is mostly taken from page 350 to 364 in the textbook, and you can skip the stuff on air masses, on El Nino. We're going to come back to that when we talk about the ocean, and also katabatic winds we're not going to get into. Midterms. Okay, the scores were posted earlier today, so hopefully you saw them. I was really pleased. I think most people did really well. As usual though, there will be some people that didn't do as well as they hoped. And it's sort of you guys I want to talk to, because if you didn't do well and you're not really surprised because you didn't do any work, then you're not the people I'm talking to. I'm talking to the people that did work really hard and are really struggling and can't understand why they're just not getting this. Okay? Now is the time to seek help. If you come and see me right now, we can do something about this. We can try and find ways to help you learn, okay? Different studying strategies, or we can just talk through things that you're finding difficult. If you come and see me in 10th week, there's really not a lot I can do. Okay? And my office hours have been incredibly quiet. I'm obviously just terrifying because no one is coming to see me. So please do make the time to come and see me if you're struggling, because now would be the time to do that. Okay? And that's especially important if you're an ESS major or if you would like to be an ESS major. Does anyone have questions about the midterm? The TAs will have the paper to hand back to you at certain times, and we'll advertise those times. And once you get the paper back, I'm actually going to get you to do a little exercise with it. I'm going to get you to think about what you spent your time studying and look at your exam paper and think where you lost marks, where you lost points, and does that actually match up with what you're spending your time doing? Okay. So, midterm evaluation feedback, thank you to all of those people that filled it in. It's really very helpful for me. So things that I will try and change. So I know there's a lot of stuff, and I am very sympathetic to that. I will really try and emphasize what I think is important by going over concepts more than once, things like that, because I know it's scary to ask questions in a big class. Most people said that they love the iClicker questions, so I'll try and put a couple more of those in to give you a chance to see how you're doing. I'll also try and post some practice part B style questions. So a few people were caught out by that sort of section of short answers in the midterm. So I'll try and post some practice ones before the next midterm to give you a chance to go through those. Okay. Things I can't change. Unfortunately, there's some things I can't change. Part of that is when the videos are posted. Lucy's doing an amazing job, and he even stays late on Friday to make sure we get our video posted. But he has a whole bunch of other classes he's also filming, and so he just doesn't have enough time in the day. So we're thankful for what you do get done. Also, this is a really broad class. It's by definition a very broad class, and I think for that reason it's one of the most challenging of the ESS classes. But it does give you a wonderful overview, but I do realize it's a challenge, and I am doing my best to try and help you with that. I think as we get towards later topics in the class, it's less conceptually difficult to understand. I think the atmosphere stuff and a couple of points in the oceans are really the tricky things, and hopefully after that it should be into things that you're more familiar with. Discussions. This was an interesting one because I had numbers of people saying they didn't like them and equal numbers of people saying they did like them. And I think it's because I haven't explained what their purpose is. Okay? So first of all, you don't have to go to all 10. 3 of them over the quarter are compulsory if you would like to earn that credit for your grade. And the reason that I set them is it's not really, the purpose of discussions isn't just to help prepare you for exams. Exams are one way of assessing you, but it's not necessarily the best way. It is our way, and it's one of the easiest ways in 400. But also important for things that cover our GE requirements are things like complicated maths, which I don't choose to do in exams when everyone's under pressure and trying to work their calculator or whatever else. I try and do that in discussions instead. And also trying to get you to think more analytically. We can't write essays or anything in this class. It's too big. So what I'm trying to get you to do is use that information, piece it together differently, and think like a scientist in discussions, something that we can't assess terribly well in exams, okay? So the whole point of the discussion activities isn't to try and necessarily teach you stuff that I'm going to test you on exams. It's to literally for you to learn and be assessed in different ways. Okay, so hopefully that makes that slightly clearer. Some things like this week really will be very helpful for exams. Okay, so I'd encourage you to go this week if you can. And if you do have other questions related to lecture, then we're very happy to go through that in our office hours. Does anyone have questions related to any of this stuff? Good, okay. In that case, let us continue with winds. Okay, so we talked about winds on, what day is it today? We talked about it on Friday, today is Monday, and we talked about how we're not going to have air moving at all if we don't have differences in pressure. In order to have wind happening, we need a pressure gradient. We need a higher pressure in one area and a lower pressure in the other. And winds always go from high to low. That's what we did with our little balloon. Air rushed out of the balloon because it's going from an area of high pressure to low pressure. The Coriolis force, remember that it would be really simple if the Earth wasn't spinning, but we are. And so we have this force that deflects air or even water currents. We're going to come back to this force when we talk about the oceans. Anything that's moving that isn't stuck literally to the surface rock of the Earth is going to be deflected as it moves. And so the main thing to remember is that it goes at 90 degrees to the right in the northern hemisphere and 90 degrees to the left in the southern hemisphere. And that's, remember, it's always along the direction of travel. So you have to look along the arrow in order to work out whether it's left or right, okay? And the way I remember it is I'm from the northern hemisphere and I'm always right, okay? So remember that. But Coriolis force is related to the speed of the wind. Faster things will experience more Coriolis force. And so if we have friction, so slowing down our wind, especially down here close to the surface, we're going to feel less Coriolis force. Okay, and this was the point we got to last week. So I wanted to talk to you, first of all, about stuff in the free atmosphere, which is really high in the atmosphere, where we can basically ignore friction. Okay, so I'm going to switch to my little diagram here, and we're just basically going to draw this diagram, but bit by bit, rather than, okay. So what I'm going to start off with is I'm going to start off with isobars, and they're going to be the simplest possible case. We're going to just have a whole bunch of isobars like that, and we're going to have a high pressure down here and a low pressure down or up there. So which way, if we can ignore everything else, which way would air move? Would it go from the bottom to the top or the top to the bottom? Bottom to the top, okay. So our pressure gradient force is not going to change. It's always going to be in that direction. It's always going to want wind to move in that direction, okay. That's our pressure gradient force. Once that air is moving, say we're in the northern hemisphere, what direction is the Coriolis force going to want to act in? To the right, and it's going to act at 90 degrees to the right. So let's draw in our Coriolis force, okay? So our Coriolis force is going to want wind to go 90 degrees like that. And so what our air is actually going to end up doing is going in between those, okay? And so once it gets to here, what direction is the pressure gradient force? It's still the same, right? It's still feeling the same force due to those isobars. So our pressure gradient force is still going to go up like that. But remember that our Coriolis force acts at 90 degrees to the direction of motion. Okay, and our direction of motion isn't vertical right now, it's at an angle. That's the way that the wind is going. So our Coriolis force is going to act at 90 degrees to the right of that. Okay, and so our Coriolis force actually acts in sort of this direction. Okay, so our wind ends up bending around a bit more. Okay, and then we still have our pressure gradient force going in the same way. We now have even more of an angle, so again, our Coriolis force acts at 90 degrees to the right, off in this direction. Okay, so our wind ends up traveling parallel to the isobars. And at this point, we have our pressure gradient force going up like that, and we have our Coriolis force acting at 90 degrees to the right, which is down that way. And when they balance out, which they do in the upper atmosphere, it just means that it keeps going in a straight line. Okay? So that's why we end up going parallel to the isobars in our high up in our atmosphere where we don't have friction. Now let's think of a case where those winds are going a lot slower. Okay? So in this case, we still have our pressure gradient force going in this direction, and we still have the Coriolis force, but it's not quite so big because it's related to the speed of the wind, and our speed is lower because we're lower down, close to the surface where there's friction. Okay, so here's our Coriolis force. So our wind is a lot less deflected. And then we have our arrow again, and our Coriolis force acting at 90 degrees to the right. Okay, so you can see how it doesn't really get deflected parallel to the isobars. It does curve around, but instead of ending up parallel to those isobars, it actually travels across them, because there isn't a balance between that pressure gradient force and the Coriolis force. The Coriolis force is weaker, and so the pressure gradient force wins, and it pulls that air across that gradient. Okay? So this is low down in the atmosphere, and this is high up in the atmosphere where there's no friction. Okay. So of course, our nice isobars are never lovely straight lines. Doesn't happen. Instead, we get more wavy lines like that. But that wind still travels more or less parallel to those isobars in the upper atmosphere. And that's as far as we're going to go, unless you want to take my atmosphere class in spring. Okay? So my question for you is, you know the air goes from high to low, and you know that it's deflected to the right in the northern hemisphere and the left in the southern hemisphere. So which two of those panels represent how air would move in the northern hemisphere? So pick one high pressure and one low pressure. Which of those represent what would happen? Okay, let's take a look. There's a bit of a split. B seems to win. Okay, so let's see if they're right. Let's draw it. Okay. So here's my high pressure in the northern hemisphere. Okay, we've got isobars going around it. Is air going to be going into that high pressure or out of the high pressure? Out of the high pressure. And which way is it going to be deflected? To the right. So as it travels out, it's going to go to the right. Okay? As it goes out, it's going to go to the right. Out and to the right. Out and to the right. So air is circulating clockwise. Okay? If we think about our low pressure in the northern hemisphere, which way is wind going? Is it in or out? In. And as it goes in, it's going to be deflected to the right. So it's going to go in and to the right. I have a problem with left and right, so be patient. Okay, in and to the right, in and to the right. So I'm always looking along the direction of motion, okay? In and to the right. Okay. So we have clockwise around the high pressure and counterclockwise around the low pressure. So let's see. Were you right? So clockwise around the high pressure is C. Counterclockwise around the low pressure is D. So yes, people that put B were right, and hopefully the rest of you now see why that's the case. And every year people try and memorize this, and it's a waste of your brain power, because as long as you know that it goes from high to low and that you can go left in the southern and right in the northern, you don't have to memorize this. Okay? So there's that summary. And we call this flow around high pressures an anti-cyclonic flow. Have you ever heard of an anticyclone? It's high pressure. Cyclonic flow is around low pressure. So things like tropical cyclones are low pressure systems. So hurricanes are low pressure systems. And just like I showed you on Friday, where we have that pattern in the high in the atmosphere, we have that movement parallel to the isobars. But where we're low in the atmosphere, what happens is that the pressure gradient force wins, and so those winds end up crossing across those isobars, okay, either in at low pressure or out. So everybody's favorite question. Okay, so I said that wind was moving into this system. So does that mean it's a low pressure or a high pressure? Low. It's a low. So I said it was moving in, so it's a low. And which way is it spiraling? Okay, so here's my low in the center here. So air is going to be moving in. And which way is it being deflected? It's going this way. It's going to the right. And so we're in the northern hemisphere here. If you went and found this system in the southern hemisphere, we'd have a low, and actually it would be spiraling in the other way, okay? So if you look at pictures of hurricanes from the northern hemisphere and the southern hemisphere, then they actually spiral different ways, and that's the Coriolis force in action. And since I have this up, I want to talk about the other question that everyone hated, which was the dew point temperature question, okay? No one liked this. So I'll show you the simplest way to find the dew point. So can anyone remember what pressure I said was, water vapor pressure was in the air? It was 5. Okay, so all I would do with that information, I don't care about the temperature, is I'd go and I'd find 5, and I would draw a straight line across my graph, okay? And where it crosses that red line, which is about here, if I could draw it properly, that is my dew point temperature, okay? So you draw a line across with that sort of value of vapor pressure, and wherever it crosses that red line, that's your dew point temperature. Does that make more sense now? Yeah, great. Good. Okay. Lots of skipping around today, but hopefully it's helpful. So we get very specific weather patterns associated with high and low pressure. And that's because at high pressure, we have air moving out at the surface. We have air traveling out in all directions. Do you think we're going to end up with a vacuum in the middle of that high pressure area? No. Okay? We're not going to end up with no air left in the middle. We're going to have to replace that air from somewhere. And the only place we can replace that air from, because we're at the surface, we can't bring it up from underneath, the only place that air can come from is from above. So at high pressure areas, we have air moving out at the surface, and that's being replaced by air coming down. Okay. So now my tricky question of the day, what happens to that air as it sinks? Are we expanding it or compressing it? We're compressing it, so what's going to happen to the temperature of that air? It's going to get warmer. So are we moving towards saturation or away from saturation? Are we moving towards the red line or away? Away. We're moving away, right? So here's our nice sort of red line, and we're getting warmer, so we're moving away from it. We're becoming less saturated. So at nice high-pressure systems, we have beautiful clear skies. We have hardly any clouds, and that's what we experience most of the time. It's one of the reasons why California, or Southern California, is basically a desert, because we're mainly sat under one of these high-pressure systems. But at low pressure, the air is rushing in at the surface, and we can't just keep piling air in the center forever. It's got to go somewhere. It can't go down because we're at the surface. The only place it can go is up. And as it goes up, does it compress or expand? It expands. Does it warm up or cool down? It cools down. Are we moving away from saturation or towards saturation? Towards. So we get clouds and we get rainfall. And so where you see low pressure systems, often that's associated with clouds and rainfall, which is what you see outside right now. Okay? So here's our low pressure cell where we get clouds and rainfall. So here's our weather map for today. Okay, this was taken from the Weather Channel website earlier because I couldn't get onto the official government one. And you can see that there's a big area of low pressure, just sort of north of our particular area. And associated with that low pressure, we have what we call a cold front, which is that blue line. And that cold air is moving down towards us in an ominous way, and it's bringing us really cold temperatures. And associated with it's a front. And remember that one of our lifting mechanisms was frontal lifting, because that cold air coming south is bumping into the warmer air that was already here, and that warmer air is rising. Okay, and we're getting clouds and rainfall associated with that. So you can just about see the isobars on there as well. Where do you think it would be windiest in the US right now? Can anyone name me a state? If I can do them, you should be able to do them. Idaho would be a good bet. Yeah, absolutely. So up and around Idaho, and I think that's Wyoming next to it, right? You can see all those isobars are really tightly packed together. And is air going to be moving into that low pressure or out? In. Okay? And there's a high pressure down here. Is air going to be moving in or out? Okay? And in which direction is it going to be spiraling around that low pressure? So I think it's going in and to the... So it should be going counterclockwise, right? How windy is it in comparison over on the East Coast? Shall we see if we're right? Okay, so have those things in your head, and I'm going to show you this really cool map that some people sent me last year or the year before, I think. And it takes basically the forecast, and it plots it. And this is the wind, and obviously the stronger those lines, the more wind there is, the faster the speed. So you can see over on the East Coast right now, it's not that windy. But you can see where that low pressure is to the north of us. You can see those winds spiraling in a counterclockwise direction. And you can see that coming from a high pressure down over Mexico. So isn't that neat? That you can basically take that weather map and you can predict what the winds would be over the whole of the US right now. So I think that's pretty amazing. Okay. No one else seems particularly overwhelmed by this, but I like it. Okay. So this is sort of the noise. This is the weather. But actually, as I said before, in Southern California, we're mainly under a high-pressure system. So there's actually some sort of background state that describes sort of the global atmospheric circulation. We get certain bands of very dry weather, certain bands of very wet weather. So let's think about atmospheric circulation now more on a global scale. Let's see if we can pin down some of the patterns and avoid some of this sort of noise that we see. So let's think about some of our early observations. So when scientists were first trying to think about this idea back in the sort of 1700s, then we had three particular observations about the Earth that we had to explain. And they're the same as today, really. First of all, people had found that there were very consistent easterly winds, and an easterly wind is one that goes from the east to the west. I know that's ridiculous, but that's just the way it is, okay? So easterly winds, and we call them the trade winds because they were used for trade. It's what a lot of the European settlers used to get from Europe across to the US, was these consistent, nice easterly trade winds. And they always blow in that direction, and they're symmetrical either side of the equator, so we have to try and explain that somehow. We also have to explain that we get this sort of band of cloud running right along the equator, and we call that the intertropical convergence zone, or the ITCZ, okay? And so we have this nice consistent band of rainfall and cloud right along the equator. So how can we explain that? And then we also have to explain this sort of bands of desert that you see. So hopefully on my nice satellite image, you can see that there's certain areas with less cloud, and they tend to correspond to, say, Southern California and Mexico, Sahara, the Middle East. And then also, symmetrically, the other side, we have parts of South America, South Africa, and this sort of area of Australia. So we have these two bands of desert. So we also need to somehow explain those. And this is sort of the simplest idea of what our circulation could be, okay? So we've talked about how warm air is less dense and so it will rise, okay? So where is air likely to be warmest on Earth? At the equator, absolutely. So it's likely to rise at the equator. Where is it coldest on Earth and likely to sink back down? The poles, okay. So that's nice in theory, but we don't see things like that. Why do you think we don't see things like that? Yep, because of the tilt and because we're rotating. We're not taking into account the Coriolis force, okay? So you can imagine that as that air tries to travel in either of these directions, we end up tilting it, okay? So this was a nice idea, but it wasn't any good. We actually had to come up with something much more complicated. And we're going to do this a bit at a time. So the first stage is that we can separate our global atmospheric circulation into what we call 6 cells. And there's 3 in the northern hemisphere and 3 in the southern hemisphere. It's symmetrical. So if you can understand the northern hemisphere, you can understand the southern hemisphere. So the first cell we're going to talk about is the Hadley cell. And this is sort of still along our nice idea that it's warmest at the equator, and so air will rise at the equator. But because the Earth is spinning, the air can't make it all the way to the pole. It actually stops and actually just goes around and around around the Earth at about 30 degrees north and symmetrically 30 degrees south. And so it doesn't go any further. What happens at that point is that it sinks back down. And do you remember what happens to air as it sinks back down? Are we expanding it or compressing it? Compressing it. Are we warming it up or cooling it down? Are we moving towards saturation or away from saturation? So we're going to get rainfall or nice clear skies? Clear skies. Okay, absolutely. So it's the same logic. So you can see that where that air sinks back down at about 30 degrees north, and then if you imagine the same thing at 30 degrees south, we have this really consistent band of high pressure. So we're adding air back down to the surface, okay? So if we're forcing air back down, we're going to create an area of high pressure. We're creating an area of low at the equator because air is rising. We're taking air away from the surface. So we have our first little cell, and you can see that as that air travels from the high back to the low at the equator, it gets deflected to the, if you look along the arrow, which direction is it? In the northern hemisphere. To the right, okay? As you go from, if you look at the Earth, and it goes from this high down to the low, it's going to be deflected to the right, and in the southern hemisphere, from the high to the low, it's going to be deflected to the left, okay? So all of a sudden, we can explain our nice easterly trade winds. So we can explain observation 1 already, okay? We can also explain why we get this band of cloud at the equator, because we have air coming together, and we also have air rising. And as that air rises, it's going to expand, it's going to cool, and we're going to hit saturation and get rainfall. Okay, so we can explain our second observation as well. And then where our high pressure is, we have our third observation, which is that we have this band of deserts, where we have mostly clear skies and very little rainfall. So all 3 of our observations can be explained just by thinking about the Hadley cell, which is pretty neat. And so the Hadley cell is what we call a thermally direct cell, which means that in that cell, where air is rising is at the hottest point, and it's cool, and it's sort of sinking back where it's cooler, okay? So let me introduce you to a second cell the polar cell, which is the nice, easy one to remember. And you can see that the polar cell, air rises at about 60 degrees north or so, and it sinks back down at the pole. Okay? So it creates an area of low pressure where air is rising, and it creates an area of high pressure where air is sinking. And that's why we have polar deserts. That's why it tends to be dry and clear at the pole. First of all, because it's just so cold we can't get a lot of water vapor into the air, but also because we have this sinking air, which is nice and stable, and so it doesn't often form clouds. So looking at that cell, are the polar cells, are they thermally direct or are they thermally indirect? So is air rising in the relatively warmer place and sinking in the relatively colder place, or is it the other way around? Okay, a few more seconds. Okay. For some reason, this is always a challenge. Okay. Where is it coldest in the polar cell? Is it at 60 degrees north, or is it at the pole? At the pole. It's going to be coldest at the pole. Is air rising at the pole, or is it sinking? It's sinking. Where is it relatively warmer, at the pole or at 60 degrees north? Is air rising there or sinking? It's rising. So in this case, air is rising where it's relatively warmer and sinking where it's relatively colder. It's doing what it should. Okay? It's the same as the Hadley cell. This is a thermally direct cell. Okay? So this is thermally direct. So let's have a look, therefore, at the Ferrel cell. So the Ferrel cell is the one in the middle, okay? And I want you to look at where air is rising and look at where air is sinking. Think to yourself, where is it warmer, where is it colder? Because you know what I'm going to ask you. I'm going to ask you, are the Ferrel cells thermally direct or thermally indirect? Okay? So where is air rising and where is it sinking? Yes? So thermally direct is where air is rising where it's warmest and sinking where it's coldest. Thermally indirect is the other way around. Okay? A few more seconds. Okay. Ooh, this is a much better split. Okay. So yes, they are thermally indirect because air is rising in this cell at 60 degrees north, where it's going to be colder than if it was at 30 degrees north. So in the previous case, we had air rising where it was warmest. In this case, air is rising where it's coldest, which makes no sense if you think about the physics of how air should move. But the key about the Ferrel cell, whoops, wrong button, is that it's actually driven by eddies. It's actually not driven by thermal energy. It's not driven by heat. It exists because the others are there. Okay? So this is a thermally indirect cell. And my favorite analogy for this is if you think of little wheels like this. Okay? So here's my Hadley cell. Here's my Ferrel cell in the middle, and here's my polar cell on the right-hand side. What would happen if I turned my Hadley cell clockwise? What direction would the middle one go? It would go counterclockwise. And what direction would this end one go? Clockwise. Okay? So that's really how the Ferrel cell works. It works because the others are there and driving it. Does that make sense now? Hopefully? Okay. So, what can our model explain? So first of all, we have our ITCZ. We have our band of cloud at the equator. Okay? It can explain our easterly trade winds. And not only that, but also we have our westerly winds either side. Okay, you can see in that Ferrel cell where we have winds going from high to low, it's deflected to the right in the northern hemisphere, and to the left in the southern hemisphere we have westerly winds, and then we have easterly winds near our pole again. It explains why we get deserts at 30 degrees north and 30 degrees south. And I wanted to show you the little video that I had at the beginning again, because you can really start to see some of these features in there. Okay. So you can start to see now we've got our nice ITZZ running along the center here. We have our easterly winds around the equator moving air in this direction. Either side of that we have these westerly winds moving material to the west, and then up here sometimes you can just see the winds reverse and go in the other direction again. Okay? And then we can also see that we don't really get much cloud and rainfall over these locations. Now look what happens if I jump forward 6 months. Okay? Do you see how that band along the equator shifted? No? Okay, let me go back. See it now? See it jumps? So in January, it was actually just to the south of the equator, whereas in June and July, August, it's slightly to the north. What do you think is causing this? The seasons, the tilt, absolutely, because where our most direct sunlight is coming in is slightly north of the equator in northern hemisphere summer and slightly south in southern hemisphere summer. Okay, so with that relatively simple model, you may not agree with me that it's relatively simple, but it is. We can explain a whole bunch of features about the global atmospheric circulation on Earth, which I think is really neat. I think it's very cool. But you can see there's a whole bunch of stuff on there that isn't necessarily easily explained with those 3 cells. And that's because we don't take certain things into account. And those things are, oops, wrong way. The circulation patterns in the upper atmosphere, they actually don't behave in reality like they should do in our model. And also, we're assuming in this case that the Earth is basically covered by water. And actually, there are land-sea contrasts. Okay? So first of all, let's take a look at what happens in the upper atmosphere. And this is important for anyone who flies around the world. Okay. Do you remember we said that warmer air, all of those molecules in that air column are going to have more energy. They're going to be moving faster, so they spread out a bit. They're less dense. So if we have our warm air column, all of those molecules are spread out, and so that air column sort of basically gets a bit taller. Whereas in our cold air column, all of those molecules are closer together, and so it's sort of a slightly shorter air column. What that means then, if we pick one particular level, perhaps that one marked by a dotted line, if we're in our cold air column, then there's basically no air molecules left above that point in our cold air column, so we're going to have very low pressure. Whereas in our warm air column, we still have air molecules above, and so we're going to have a higher pressure at that place. Okay? So that means that if we plot it, so up here is the pole, up at 80 degrees north, down here is 30 degrees north. Because our warm air column is more spread out, it's less dense, we don't have as much of a pressure gradient as we go up in the atmosphere. Our isobars, as we go up vertically, are more spread out. Compared to the cold air column, where all those molecules don't have as much energy, they're closer together, and so we see a bigger pressure gradient as we go up in the atmosphere. And if we pick any one particular location, perhaps that one I've marked with the big red arrow, you can see that at 30 degrees north, our pressure would be 800 millibars. In the cold air column, at the same altitude in the atmosphere, it would be 700 millibars. So we're creating this large-scale pressure difference, actually on sort of a global scale within the hemispheres. Okay? So which direction would air move in? To the pole or to the equator? to the pole. We've got higher pressure where it's warmer. So air is wanting to move towards the pole, okay? But we're in the upper atmosphere, so it's actually going to be deflected. So if we think about where we're going to get the most intense difference between hot and cold, okay? So if we have a really hot air column next to a cold air column, we're going to see a really strong difference in temperature and therefore pressure, and therefore we're going to get really strong winds. And one of the most obvious places where that can happen is if you can imagine that the surface winds in our Ferrel cell are moving up from sort of 30 degrees north from our deserts. They're really nice and warm winds moving north. And if you look at the polar cell, at the surface winds of the polar cell, we've got this really cold air coming south from the pole. So where those two surface sort of air masses meet, we're going to have a really sharp temperature gradient from warm on one side to cold on the other side. And that really sharp change in temperature also equals a really sharp change in pressure. Okay? So here's our warm on the right-hand side and cold on the left-hand side, and you can see that we get this sort of really steep gradient. Okay? And what happens is that where that happens, where we get that really sharp change, we have really, really, really strong winds, and we call it the jet stream, the polar jet stream. And it forms at the polar front, which is basically just the meeting point between the Ferrel cell and the polar cell. And who's heard of the jet stream before? A couple of people at least, okay. And you've heard of it because you probably fly, okay? So here's my little diagram showing January and July and the isobars in the upper atmosphere. So this isn't at the surface. This is high up in the atmosphere. And you can see, when do you think it would be windier? January, because we have this much sort of larger change in temperature at that time. And so, if we're going from higher pressure at the equator to lower pressure at the pole, which way do upper winds blow around that North Pole? Do they go counterclockwise, so to the east, or do they go clockwise to the west? Is that right? Yes. Yes. Okay. So have a think. Talk to your neighbor. Which way do you think they grow? So it's low pressure at the pole and high pressure down near the equator. A few more seconds. Okay, let's take a look. Hopefully people are getting good at this by now. Doing reasonably well, okay. So they go, actually, hang on. Yes. Sorry, I have to really think about this sometimes as well. Absolutely, so they go to the east, okay. So they look like that. They circle around the Earth. So my other question for you is, okay, I'm going to go back to the UK next summer. Which way will be the fastest when I fly home? Will it be from LA to London, from London to LA, or are both of them the same? So think about where LA is, think about where London is. You don't fly across the Pacific, by the way, across the Atlantic. Okay, a few more seconds. Okay, so let's take a look. See how many people have flown around. Everyone knows where London is, right? Okay, so let's go back a second. So where is LA? So LA is down here on the coast here. London is over here. So which way will be quicker? Will it be when I go from LA to London, or on London to LA? It would be actually be LA to London, okay? Because I'm going with the wind. On the way back, we're fighting against the wind. And actually this saves the airline industry billions of dollars probably, because it can make up to an hour difference to your travel time. Okay, so if you often see is that if you fly across the Atlantic, not quite done yet. If you fly across the Atlantic, you'll often see that you take a very different path going to coming back. And it's due to the position of this jet stream. You'll try and get in that jet stream as you go across, but you'll try everything to avoid it coming back. Okay? So there you go. Next time you fly, make note of that. Okay. So second thing that I wanted to mention is that we have differences in land-sea distribution. So you can see this is the northern hemisphere, and this is the southern hemisphere, and a lot of our land, most of our land, is actually in the northern hemisphere. And as you know, if you've washed up, your washing up liquid stays warm, and it sort of takes longer to heat up than, say, cutlery that you lift in and out. So the land and the ocean respond differently to heating. The land will heat up and cool down differently than the ocean, and that causes little local wind patterns, and that's what we're going to talk about on Wednesday. Okay, thank you guys.